After 2.5 centuries of helping humans make better predictions, one of mathematics' most powerful tools just got a mind-bending quantum upgrade that could revolutionize how we think about probability itself. Imagine if the very foundation of how we calculate odds and make educated guesses, a principle that has guided everything from medical diagnoses to weather forecasts since 1763, suddenly needed to be completely reimagined for the bizarre world of quantum physics. That's exactly what happened when an international team of brilliant researchers decided to give Bayes' rule a quantum makeover. And the results are nothing short of extraordinary. But here's where it gets controversial. Some scientists have long argued that probabilities should be completely objective, stripped of any human beliefs or subjective interpretations. Yet, Bayes' rule has always been built on the radical idea that what you already believe matters when calculating what might happen next. Professor Valerio Scarani, who serves as Deputy Director and Principal Investigator at the Center for Quantum Technologies, doesn't mince words about the significance of this breakthrough. I would say it is a breakthrough in mathematical physics, he declared confidently. Working alongside Assistant Professor Ge Bai from Hong Kong University of Science and Technology, and Professor Francesco Buscemi from Nagoya University in Japan, Scarani's team published their groundbreaking findings on August 28, 2025, in the prestigious Physical Review Letters. Bayes' rule has been helping us make smarter guesses for 250 years. Now, we've taught it some quantum tricks, Professor Buscemi explained with obvious enthusiasm about their achievement. What makes this discovery so remarkable isn't just that they created a quantum version of Bayes' rule. Other researchers had attempted similar quantum adaptations before. The game-changing difference: this team became the first to derive their quantum Bayes rule directly from a fundamental mathematical principle, giving it unprecedented theoretical foundation. Understanding the classical foundation. To truly appreciate why this quantum leap matters, let's first explore what made Thomas Bayes' original concept so revolutionary back in 1763. When Bayes first outlined his rules for conditional probabilities in his famous work, An Essay Towards Solving a Problem in the Doctrine of Chances, he introduced a completely new way of thinking about uncertainty. Consider this everyday scenario that perfectly illustrates Bayes' power. Imagine you wake up feeling slightly under the weather and decide to take a flu test. The test comes back positive, but here's the crucial question. How worried should you actually be? Most people would assume a positive test means they definitely have the flu. But Bayes' rule reveals a much more nuanced reality. The probability that you actually have the flu depends on several interconnected factors. The accuracy of the test itself, how likely the test is to give false positives, the current flu prevalence in your area, and, this is the controversial part, your initial gut feeling about whether you might be sick. This approach treats probabilities not as fixed objective facts, but as expressions of our degree of belief about what might happen. This interpretation has sparked heated debates in the statistical community for centuries. Traditional statisticians often argue that probabilities should be completely objective, based purely on measurable data without any subjective human input. And this is the part most people miss. Bayes' rule has become incredibly successful precisely because it acknowledges that human beliefs and prior knowledge play crucial roles in making predictions. This is why the approach has found explosive growth in fields ranging from medical diagnosis and weather prediction to the artificial intelligence algorithms that power everything from search engines to recommendation systems. The minimum change revolution. At the heart of Bayes' rule lies a beautiful and intuitive principle called minimum change. Think of it as nature's way of being conservative with updates. When new information arrives, this principle ensures that our beliefs change in the smallest possible way that still accommodates the fresh evidence. Mathematically speaking, The principle works by minimizing the distance between probability distributions before and after receiving new information. But what does this actually mean in practical terms? Returning to our flu test example, if your test comes back negative, Bayes' rule wouldn't suddenly declare you perfectly healthy. Instead, it would adjust your beliefs about having the flu downward in the most modest way possible, that's still consistent with the negative result. You become less likely to have the flu, but you don't completely rule out the possibility, especially if you had strong initial reasons to suspect illness. This conservative approach to updating beliefs turns out to be remarkably effective at avoiding dramatic overreactions to single pieces of evidence. Which is why Bayes' rule has proven so valuable across countless applications. Quantum mechanics meets ancient wisdom. Here's where the story takes a fascinating turn into the strange world of quantum physics. The research team realized that quantum states, much like classical probabilities, contain information about the likelihood of different outcomes. When you measure a quantum particle, you only discover it at one specific location. But before measurement, its quantum state describes the probability of finding it at various positions. This creates a perfect parallel to the classical Bayes situation. You have prior beliefs, represented by the quantum state. You gather new evidence through measurement, and you need to update your understanding accordingly. Professor Scarani and his colleagues approached this quantum challenge by focusing on a quantum analog of the minimum change principle. Instead of minimizing distances between classical probability distributions, they worked with quantum fidelity, a measure that captures how similar two quantum states are to each other. The team's breakthrough came when they derived the quantum Bayes rule by maximizing the fidelity between mathematical objects that represent forward and reverse quantum processes. This maximization of fidelity is mathematically equivalent to minimizing change, creating a beautiful quantum parallel to the classical minimum change principle. A stunning validation of previous work. But here's where the plot thickens with an unexpected twist. When the researchers worked through their mathematical derivations, they discovered that their equations matched something called the Petz recovery map in certain scenarios. This recovery map was originally proposed by mathematician Dennis Petz back in the 1980s and had long been suspected by quantum researchers as a likely candidate for a quantum version of Bayes' rule, based purely on its mathematical properties. This is the first time we have derived it from a higher principle, which could be a validation for using the Petz map, Professor Scarani explained, highlighting the significance of providing theoretical foundation for what had previously been educated speculation. This connection between their principled approach and Petz's earlier work provides compelling evidence that they've identified the correct quantum generalization of Bayes' rule, a validation that could have far-reaching implications for quantum computing applications. Revolutionary applications on the horizon. The practical implications of this quantum Bayes rule extend far beyond abstract mathematical beauty. The Petz recovery map, now backed by solid theoretical foundation, shows enormous promise for quantum computing applications, particularly in two critical areas: quantum error correction and quantum machine learning. Quantum error correction represents one of the biggest challenges in building practical quantum computers. These machines are incredibly sensitive to environmental interference, and developing methods to detect and fix quantum errors without destroying the delicate quantum information is essential for creating reliable quantum computers. A properly grounded quantum Bayes rule could provide new tools for this crucial task. Similarly, quantum machine learning, the intersection of artificial intelligence and quantum computing, could benefit enormously from having a principled method for updating quantum beliefs based on new quantum information. The research team isn't stopping here. They're planning to investigate whether applying the minimum change principle to other quantum measures might reveal additional solutions and applications, potentially opening entirely new avenues for quantum information processing. A question that challenges everything. This brings us to a thought-provoking question that goes to the heart of how we understand reality itself. If our most fundamental tool for reasoning under uncertainty needed a complete quantum overhaul, What does this tell us about the nature of knowledge and belief in a quantum universe? The classical Bayes rule assumes that we can cleanly separate our prior beliefs from new evidence. But quantum mechanics suggests that the very act of observation fundamentally changes the system being observed. In a quantum world, can we ever truly separate our beliefs from the reality we're trying to measure? This quantum version of Bayes' rule doesn't just represent a mathematical advancement. It forces us to confront deep philosophical questions about the relationship between knowledge, belief, and reality in a fundamentally quantum universe. What do you think? Does this quantum evolution of a centuries-old principle change how you view the relationship between subjective beliefs and objective reality? Are we on the brink of a new era where even our most basic reasoning tools need quantum upgrades? Or is this just an interesting mathematical curiosity with limited practical impact? Share your thoughts. This is exactly the kind of breakthrough that deserves vigorous debate about its implications for science and philosophy.